We're 5 minutes early. Do I get the extra 5 minutes, or I should still stick to 20? No, I'll stick to the 20. I just want to make clear, if I make any sarcastic comments, which I am prone to do in front of a podium, I no longer officially represent the Canadian Conservation Institute, which is both a great loss but a great pleasure, in order to be able to speak purely as independent opinion. I hope that doesn't mean that it's just an irrational opinion, but I just wanted to make clear, especially for any future videos that may live forever online, this is not a Canadian Conservation Institute lecture. On the other hand, I really have to say everything I know about the field, pretty much 99%, was developed when I was being paid for by the Canadian taxpayer at the Canadian Conservation Institute. I'm going to give a bit of history, quite a bit of history, although it's a bit of a potted history. I get the impression going through the program and the authors that there are a number of gray-haired eminences here who know this stuff backwards and forwards, permission to doze off and catch up on jet lag. On the other people, I feel that there are a number of people from fields that have just been thrown into doing the science for us and perhaps haven't had the time or the inclination to see where a lot of this concern in the museum world has come from. And the fact that it's a very old story. 1872, we already have the fundamental description of what this whole 3 days is going to be about. So that's 150 years ago. The argument about glass or not glass is also old. National Gallery in London first put it on to protect from heavy pollution from gas lights. And in the 50s, the curators decided that there was no need to keep them on anymore. But as I will show, they're secretly reappearing on many of the walls of the National Gallery without fanfare. At the Tate, it occurred with fanfare, not at the National Gallery. Also, the idea of controlling humidity by an enclosure goes back to Rathken. It was for bronze disease and showed that low humidity would prevent so-called bronze disease. But also there are drawings there on how to place the sorbent, how to make sure there's enough holes, how to make a functioning sorbent-controlled enclosure, which also controlled pollution. Again, over 100 years. We're going to jump ahead relatively to 1908. McCabe was an engineer who specified 55 to 60% relative humidity. In the Boston Museum of Fine Arts. Followed in 1914 and 16, we believe that the Cleveland Museum of Art was the first purpose-built building with winter humidity control in mind. In 1954, I purposely show this like a monolith because it's a little booklet, but it's hugely significant in the field that we're addressing in the next 3 days. And I hope all of you at some point find a copy and read it. It'll take an hour or less to read it. And you will recognize many of the issues, you will recognize many of the perspectives, and you'll also recognize some really bad experimental design, which should make you feel better about your own experimental design. Oops. Okay. This is the opening and the foreword to the Courtauld booklet, in which the director of the gallery speaks about, rather evasively or rather obscurely, about why they suddenly needed to have a meeting and do research. It just says, oh, we asked people to do research on it. Seems like a plausible thing. If you go into the later chapters where the reports are provided by the engineers and researchers at Her Majesty's Department of Works who specialized in forest products and wood, you will find some of the causes. Oh, sorry. Before we get to that, the other remarkable thing about this study is, I hope you can read that, 10 painted panels of the 14th to the 15th century were donated to the experimental cause. And if you're wondering how they carefully worked with them to avoid damage, they first cut them up into 1-inch wide strips. And then they did a nice study where they scraped off layers one at a time to see how it changed their moisture response. So they scraped off the varnish, and then they took off the paint, and then they took off the ground, all the time sealing the edges and back so that that wasn't interfering. So it's actually the only and probably best data on thermal hygrometric response time of an authentic, no question about it, panel painting. This is the reason the study was done. They noticed that the panel paintings were getting damaged much more than usual. I mean, I love this statement for two things. What's usual? Usual was the fact that this building was not humidified anyway. And exceptional because it was the coldest winter on record in 1929 in London. I checked the weather records, and it was indeed substantially lower than normal. These are the response times. They did eight days of dry, 10 days of high humidity, and the different plots you see are for the different state of the scraping off of the coatings. And it's roughly 8 to 10 days for almost 90% of response. So if you're ever looking for uncontrovertible data on response of authentic materials to moisture, there it is. The contribution from the Canadian National Gallery was this. This was a drawing dated 1934, which is how we date the publication, because there's no publication date on the frontispiece. So in 1934, it came out. And this was a hermetic, moisture controlling glass fronted case for panel paintings in Canada, which had heated and unhumidified gallery. And something like this has continued to the present day, although rather than brass, it's made with aluminum. So this is what happened in 1929. There was an unusually cold winter. The Thames apparently froze over for the first time in living memory. And I show the people in coats from 20th Century Fox to remind you that in those days, people kept their coat on. The National Gallery stated in this booklet that they maintained 60 degrees Fahrenheit during the winter inside the building. You were expected to wear a coat when you walked through the gallery. So that actually helped to some extent reduce the low humidity issue. I did some calculations based on the reasonable estimate of the moisture content of the air from the weather records, given the temperature, then worked backwards onto what humidity that would give at 60 degrees Fahrenheit. And it comes out around 20%. Now, in those days, in the booklet, they state that they try to maintain 60% in the summertime. So these are the days of 60% being the notion of a middle value. So this is a 40% relative humidity drop. This is not a small humidity fluctuation. This is a crash, and what I will later on call an extreme event. It's also, I think, the last time any gallery admits to having an extreme event where they see damage. I just don't believe it hasn't happened again somewhere in the world, if not in many places in the world. People just don't report it. Or you've probably heard this one, but those of you coming into this area new, very many monitoring systems for climate in museums are operated and piggyback on the HVAC system. So when the power fails and the HVAC dies, so does the monitoring, which is a very handy way never to have nasty monitor records. Whenever your system crashes, you have a blank straight line because they're not monitoring anything. And it's remarkable how many places still are caught in that trap. All right, we leap ahead now to the origins of the magic numbers. This is an article in 1942 by Rollins in the Museum's Journal. And here's the kicker, which incidentally is easy to remember. So he knew that having easy to remember round numbers like 6060 if you're using Fahrenheit was really handy for people to get a grasp on what their target should be. So this is the beginning of the so-called standards, or what we should probably better call habits of our field, which fossilized for a long period of time. This is Gary Thompson in 1981. I had the pleasure as a young conservation scientist to visit the lab during an ICOM meeting. Many people have pointed out that his first edition doesn't have any magic numbers. It essentially is 200 pages of you should think about this and then make a decision for yourself. And that, I think, is where we're trying to get back to with a whole lot of more technical information. But it's going to be a struggle to deconstruct and come back to Gary's perspective. I think it's fair to say that my institute has a certain amount of responsibility for fossilizing the guidelines. Ray LaFontaine, in one of the early technical bulletins from the Canadian Conservation Institute, picked out a number for humidity, and then actually pointed out later in the same publication, that's probably too extreme. We need to open it up because Canadian winters are so harsh. And by the way, our own building could not tolerate what we were recommending to other museums. So we thought it was hypocritical to suggest they maintain something that the flagship institute couldn't. We still had to do a complete retrofit 20 years later with mold reduction in the walls that were completely riddled with mold and dangerous spores. So actually 38% still didn't save the walls in a building that was never designed for it. So I've included both measurements of temperature. And then in his second edition, Gary Thompson quoted Ray LaFontaine, and I think he got pushed by people saying, why isn't there a page in your book I can cut and paste into an architectural program, which is what people do in capital projects. So he did put his appendix in, and that's where 50% got settled on as a nice middle value rather than 60. And these are temperatures you can find, or a temperature you can find in one of the versions of the appendix, but then there's kind of another version which says, well, maybe a little wider. So a very wide range, much wider even than what we call BESO, which I will get to in a few minutes. But those were the whatever 8 commandments of our field. In the 90s, their research into mechanics began again. Again, I mean, after the Courtauld excitement and researchers from outside the field being involved and doing pretty systematic, partly goofy and partly useful research. I have time. One of the goofy things they did was they tried to simulate the curvature they saw in panels. And they said, well, we don't have time to wait around for the curvature to occur over many cycles by humidity response because we'll be here until we're dead. So we'll put it in a machine and bend them. And that was already a little bit iffy about telling you anything useful. And then they said, we're going to warm it up so it goes faster. Now, if you know anything about mechanics, you know that warming it up will do the opposite effect. It'll make everything nice and rubbery and tell you nothing about fracture. And that's what happened. And a lot of this data was compiled. This is a review I did of data that's from numerous people in the audience, beginning with Mary Mecklenburg's data in 1981. The work I did with Debbie Daly Harton in 87 and Headley, and then Cecil Anderson's work by 2014. And they're all the same sort of hockey stick. We can argue and get heated about exactly where the trough is, but the fundamental shape is the same, and it's become ground zero. And then in 1999, the ASHRAE committee settled on these familiar codes, and I'm not going to go into what they are. I just want to give an overview of how we got there. Bezo Group said, this is what they said we could live with. There was a meeting of British standards. They had created an interim booklet. It kind of returned to think. There were a lot of complaints that I saw in the reviews, initial reviews of the draft, saying it's too much head scratching. Where are the numbers? And then in 2019, a lot of risk management ideas were added to the ASHRAE chapter. So I'm going to jump into a few minutes of risk assessment. And main point of my talk is comparing from small, frequent versus large, rare fluctuations. We actually had an exercise that some of you might have seen on Zoom last week where I had a sort of real painting. It was real in terms of being solid. It wasn't real in terms of being a great painting. But the question was, what kind of magnitude of risk would you give? It was a crash course in a particular method or scale, ABC method. That's not really important at this point. I'm just going to explain that anything in the red is really catastrophically risky. Orange is not good. Yellow is borderline. And I asked people to rank or to vote on a score of 1, 2, 3, 4, 5 on how much loss of value there is, either from Bezo fluctuations for a whole 100 years. There are many of us in the room who think that's not going to give any risk, but that's not how many other people in the museum feel. So this is addressing their perceptions as much as anything. And then an extreme fluctuation, which people judged would happen actually every 3 to 10 years, which again, they were very cautious numbers. This was, the red bars are for how often or soon it's going to happen. So obviously every 30 years is worse than something that takes 100 years to add up to anything. These are the estimates of the loss of value. And this is assuming it applies to all 1,000 paintings in the collection. This, for reference, is my own votes on what it would be, which I think I have just a lot more practice in using these scales. But the uniformity thing I want to point out is the completely neophyte to voters looking at this, museum staff and people on Zoom, mostly conservators, about half conservators, but also curators and art historians and managers. They did say that it's at least, they saw 30 times difference, 30 times more risk for the rare events. I see it as more like 300, given that not everything in the 1,000 paintings might have 10% that are going to be affected by Bezo. And if they were affected, it's going to be a trace effect. But the point is just that it's very different. And the other thing I want to point out is in these museums in Italy, you can find panel paintings that have not been restored. And you can see this one has a crack. It's a little bit dusty and not glossy looking anymore, but it's near the front door of the museum gallery Palazzo in Rome. And this is another painting which has been, beautifully restored. And you can see that those of you maybe close enough, you'll see this whole area has got trateggio. It's an infill, and around the edge of that infill with the trateggio are all of the flaking and breaking. So the other point I want to make is not only are small, moderate-sized fluctuations less damaging, the only thing they're going to damage are recent restorations. The likelihood that you actually flake and pop artists' original paint when it's been through 400 years or 300 years is negligible. So when we have very tight control, we're either protecting incredibly badly designed, made recent art, which occasionally happens, or infills and repairs. Not that it doesn't cost to repair a repair, but briefly, we need to be able to integrate the design and strategies for all the layers of enclosure. This is a diagram from a talk I gave at the Engineer Society, ASHRAE, some years ago. This is the old Mona Lisa case with silica gel at the bottom. That was when you could actually get your nose up to the close to the Mona Lisa without people in the way. This is at Anne Frank house. Obviously, the diary needs to be in a case. This is at the Tate, the Whistler. I'm showing in yellow where the glass is. It's non-reflecting. The whole hatred of glass seems to me can be greatly abated by non-reflecting glass, which is available in much bigger sizes and lower costs than it used to be. This is my second last slide. Lukáš. This is, I published in a paper on backing boards, which was in an Italian conference organized by a group called Sesmart Sette, which has done some very nice work in their publications. And they're anxious to bring science and conservation science from the rest of the world into Italy. So this was a calculation I did based on the leakage model, which I'd published many years earlier, which demonstrates that in an enclosure with a painting with a wooden frame and a layer of canvas, you don't need extra buffer. You really just need to watch leakage rates. And what you can see at the top is if you're willing to use glass and be careful, you can get 15 years response time. And on the other hand, if it's just a backing board, it's 1 to 2 days. And if it's a leaky backing board on glass, the glass is a waste of time because the backing board's leaky. But what I want to show here is a gigantic orders of magnitude range in leakage based on very small design and fabrication details. Thank you.
Thank you, Stefan, and I'm sure that there will be questions. Who wants to ask questions?
I mean, I can take questions about things that are other things that I didn't address, which you may think know that I can address. That's fine. I really thought it was necessary to, at the beginning of this conference, to put us in context. It's 1930. It's almost exactly 100 years since that first extreme event, which triggered the first conference on the mechanics of paintings in response to humidity fluctuation. And our field has gone in fits and starts since that moment. The only thing that seems to have really stuck is the success of magic numbers, the success of an extremely risk-averse set of numbers, which frankly emerged out of I don't know what exactly. I did get... My first boss was Ray LaFontaine, who wrote the publication where they first used a plus-minus symbol. Our CCI technical bulletin is the first time I found the plus-minus nomenclature. And I asked him, where did the ±3 come from? Oh, and by the way, his second initial is H, so his name is R.H. Lafontaine. So you can't just question his advice on relative humidity when it's already in his name. But he was a totally chill guy, chemist, and he was just doing the best he could after sitting down with other conservation scientists at the moment. And he said, it's the switching differential of a medium-priced hygrostat. We can't ask for better control than what's a hygrostat will switch on and off. So I kind of said, well, that's nice, but there's a lot of steps between what the hygrostat's differential is and what actually the room performs at. And anyway, that is a best performance model. And it's true. If you look at the pollution recommendations, they were all best technology solutions, best technology. And the trouble is people lost track or never knew that the specifications were really best available technology. They were not, we know anything more than this will damage the collection. And so it's been an uphill battle because our field, and I do want to point out that I'm half scientist, half conservator. I trained at the Masters of Conservation in Queens as an objects conservator. I interned in museums. I worked with the paintings restorer for 20 years, making gadgets and low-cost suction tables. I have a foot in both camps, and I want to reconcile what seems to be sometimes a split between experience and evidence of the caretakers, conservators, and that of the scientists. What I wrote recently somewhere else is that the conservators are the keepers of the best evidence, and the scientists are the keepers of the best models. And we clearly need to synchronize those two aspects.
So,
yeah, question from Rob.
from Cecil.
Cecil.
Thank you. Thank you for pointing out the extreme events. I agree with you completely. And I know of places where they happen without being reported. So can you talk to us a little bit about the Bezout temperature requirements, if you want to call it that?
Yeah.
Why they're not lower? I mean, in Denmark, we do have cold storages to save energy, and some people are worried about that, and we tell them that this is for human comfort. Am I right? Why are they not being changed or debated more?
It's true that people latched onto the stability is best. When Burmeister, the Derner, reacted to a conference that Stefan Simon had organized where people were saying things like, stability isn't the only thing, he post-conference came out with a manifesto, basically, I think it said, quote, stability is best. And unfortunately that stuck. And when you do the modeling, it's much more complicated than that. And the short answer is not really. The temperature issue was they took a small fluctuation because the community assumed that fluctuations were bad because they had seen damage from gigantic fluctuations. There was a problem of extrapolating to smaller values and believing that it was infinitely extrapolatable to, plus minus 1% must do a little bit of damage. So that's what we're trying to undo. The temperature one, well, we just added on human comfort pretty much. There have been a couple of little wrinkles. The audiovisual people with magnetic tapes believe, and there's some evidence that at below 8 degrees centigrade, 40-something Fahrenheit, that some of the waxes and lubricants will be exuded. That said, my understanding is it's not very difficult to remove wax from a tape So in 100 years, you either have tape that's brown and sticky and unplayable, but the surfactant didn't migrate, or you've got something that's playable as long as you clean the surfactant off. So I don't think that idea has been thought through fully, for example. We also recommend not taking acrylic paintings below 5 degrees because they really start entering they're on the knee of their rubbery, of their leathery to glassy transition. Oil paintings is a little lower and it's less pronounced because with pigment it's already acting pretty stiff most of the time. But yes, people need to be careful with a painting below 5 degrees. There's some discussion as to whether they will spontaneously or due to temperature shrinkage fracture. I'm not a strong believer in that, but it's plausible. If it is true, I would say it's another reason not to over-key out a painting. The days of thinking that when the painting's a little saggy in high humidity, it's a great idea to hammer the keys. It's a bad idea. Let it sag when the humidity's high, and it should be just snug when the humidity is as low as your place goes. And that will solve most of that. Because we know the dimensional change with temperature is very small compared to the humidity one. So, just like a 0.5 millimeter movement on a stretcher would drop the thermal stress out. Did that answer your question to some extent?
Okay, we have time for the last question.
Great presentation, so thanks a lot. Also, in my experience, extreme events are really the key. And I did have an experience in a collection store of 100% humidity for 18 hours. In a survey to look for damage, I didn't find any, even though there were a lot of things on open shelves. I guess I have a two-part question, but this is the lead into that. Other ones are, if you're in a recent mammal or subfossil collection, when winter humidity gets extremely low, you hear things cracking in the cabinets. And so, you could look at your, if you have a hygrometer in a cabinet, you could time it with the cracking and find out the critical event or critical humidity. But what I'm wondering is, for this 1929 event, do we have any idea of how much loss of value there was to the collection after it went through that? And are we getting any better at that? If there was another extreme event, would we do better than me just poking around in a collection store and seeing if I can see anything?
Thanks for that, Rob. For those of you who don't know, Rob Waller from, let me get your company name right, Heritage. Protect Heritage probably has the most field experience of anyone in the world on quantified risk assessment of museum collections. And I believe is fully available to be hired by those of you who wish to do. Unlike myself, I have to tell people over and over, I'm a provider of tools and methods. I couldn't do it at CCI, and I have no inclination to. That's not where I'm most valuable in my productivity at the moment. So speak to Rob if you want somebody to handhold you through a complex risk assessment. I think those kinds of observations, Rob, it's really important to make conservators comfortable with revealing them. I remember certain persons 20 years ago, a well-known scientist in our field who's not in this room, just coming down like a ton of bricks on somebody's story and said, that's anecdotal evidence, as if it was obvious that anecdotal evidence is garbage. Anecdotal evidence is one data point, and it can be a really great one if you know really what the humidity was. The problem is people will report observations that are actually linked to a much earlier event. But at face value, it's anecdotal evidence or what Jim Drusick was trying to do in terms of using medical models or looking at epidemiology and so on. It's all going to come back to collecting that kind of evidence from collections in hand with systematic research. But in the end, the conservator, the museum community is not going to feel really comfortable. And uncertainty is the painful part of risk assessment that all humans avoid. We need to get as much comforting evidence as possible.
Stefan, thank you very much. Please join me in thanking Stefan.